Hi, and welcome to video 4B, which is Addressing and Local Area Networks. In our 4A video, we learned about the getting a signal sent from one computer that another computer could understand. And we learned a little bit about the topology of the networks, how they might be connected. But we didn't really address how the signals actually get sent from one computer to another, and how a computer knows what of all the stuff coming across the wires or across the airwaves, what it's supposed to be looking at. So we're going to get into addressing. You can think of this as analogous to the fact that you might write something down on a piece of paper, but to get it from you to me, you have to stick it in an envelope, address it, put a stamp on it, and then put it in the mail, and it gets delivered. We'll start talking about that addressing and delivery mechanism in this video. So let's get going. Now, addressing other computers. If you built a local area network, you could give each computer a unique name. You could call it Megan's computer or Maddox's computer, and then develop a protocol for sharing frames of information where the frame header included the name of the computer it came from and the one it was headed toward. In fact, early networks did this. This works very well if you can control all the names. If you know it's just going to be used in your local office and you've got 12 people and you know the names of their computers, you can do it that way. But what if you want your network to connect with other networks and you can no longer guarantee that computer names are unique? It gets a lot tougher then, doesn't it? So, addressing computers in a wide area, every network device in the world has a unique hardware address. Think about that. This is a true statement. Every network device in the world has a unique hardware address. Your mobile phone has a network interface device built into it that's got a unique address. Your laptop has a network interface card, either separate or built onto the motherboard, that has a unique address. Every piece of hardware in the world has a unique hardware address. It used to be called the Media Access Control Address, or MAC address, but it isn't always called that anymore because it's confusing. It doesn't really have anything to do with Apple Macintosh. Your Windows PC has a network interface card that has a MAC address, and it doesn't have anything to do with Macintosh. So it's sometimes still called a MAC address, sometimes it's just called a hardware address. These hardware addresses are 48 bits long. Okay, 48, a string of 48 zeros or ones. That means there's a total of 2 to the 48th unique pieces of hardware that could possibly communicate with each other. 281 trillion, a little bit more than that. 2 to the 48th is about 281 trillion. That's a lot of devices, okay? There's got to be a better way than to have to know up to 281 trillion devices to say, I want to get my machine to talk to the Global Online Academy server to give me this particular web page that I'm looking at. If you knew the hardware address of every single computer you were going to interface with, it's possible to set up a network protocol that sends frames of information out on your network with that hardware address. And every computer could check every frame that came and see if that frame was addressed to them. This would be really hard to maintain. What if, for example, YouTube changed its physical servers? They upgraded, they bought a new machine, they now have a new hardware address. Wouldn't you still want to connect to YouTube without you having to change? If YouTube decides to upgrade to a faster network card, that's their business. You should still be able to get to them. So, enter IP addressing. IP stands for Internet Protocol. When the Internet's precursor, called the ARPANET, was created, and that was by the United States Department of Defense's Advanced Research Projects Agency. That's the ARPA of ARPANET. When it was developed in, I believe, the early 1970s is when the work was first happening. One of the protocols they developed was the Internet Protocol. IP addresses originally consisted of 32 bits. This allows about 4 billion unique addresses. The original ARPANET developers couldn't imagine possibly that number ever being exhausted. It just was foreign to them. At the time, there may have been about a few thousand computers in the entire world. Now, you've got probably a phone and a home computer and a school computer and an iPad and all sorts of things that all have IP addresses. Multiply that by 6 or 7 billion people in the world, and you're going to run out of 4 billion unique addresses. Okay, but IP addresses originally were based on 32 bits, and much of the time today are still using just those 32 bits. Now here's how an IP address, a 32-bit one, works. These are also called IP4 or IP version 4 addresses. The 32 bits are divided into 4 groups of 8 bits. They're called octets. The convention is to represent each octet as a decimal number because humans don't like spelling off 0101000011111001100110001. We can't remember things like that. But if we took 32 bits, here's an example of 32 bits, here's 8 of them. Turn this 8 into a decimal number. Well, how do I turn a binary number into a decimal number? Here's the ones place. Here's the twos place. Here's the fours place. Here's the eights place. You notice each time the place is getting bigger by a factor of 2. Here's the 16s place. Oh, okay, I've got 16. Here's the 32's place. Nope. Here's the 64's place. Okay, I've got 64 and 16. That's 80. So we call that first octet the number 80. The next one. I've got a 128, a 64, a 32, a 16, an 8, and a 1. That adds up to 249. A 128, a 16, an 8, and a 1. That adds up to 153. A 2. That adds up to 2. So this IP version 4 address we would call 80.249.153.2. I'll bet you've seen numbers like this. It's called dotted decimal notation, but it's just a way for humans to understand 32-bit numbers. Now, since we're running out of 32-bit numbers to use, IP version 6, now I don't have any idea what happened to version 5, but IP version 6 addresses are 128 bits long. These 128 bits are grouped into 8 sets of 16 bits each. Each set of 16 bits, which you can call a hextet, is generally written as base 16 digits, hexadecimal digits. Now, if you are not used to hexadecimal, we know the decimal system. We use digits 0 through 9 and base 10 system, so each position, we have a ones position, a tens position, a hundreds, a thousands. In base 16, we need to have 16 digits. Once we get from 0 to 9, we start using letters. So the letter A means 10, the letter B means 11, and so on up through the letter F being 15. Now, if we let's just look at this first hextet. The ones place, the 16's place, the 16 squared, or 256 place, the 16 cubed, that would be 4,096, no, 2,048, maybe it's 4,096. I can work it out in my head, but it doesn't matter. We don't have to. 2001. Hexadecimal digit, hexadecimal digit, hexadecimal digit, hexadecimal digit. You notice when I go through here, sometimes I get letters instead of numbers. This is how you write an IPv6 address. But sometimes there's a lot of zeros in there. So to make it easier for humans to understand, leading zeros in a hextet can be dropped. So 0800 I could just write as 800. 00CF I could just write as CF. And any number of consecutive 0000 hextets could be replaced just by 2 sets of colons. But you can only do this once per address. So this 00000000, I could just drop that out and leave this colon and this colon. I can only pull that trick once per address, because suppose these two were also 0000000, and I did it, I wouldn't know was I dropping out 1 set or 2 sets or 3 sets of 0000. Now, this example up here, if I wanted to write it in a shorter form for humans, becomes 2001 : 3210 : 800 : 200C : CF : 1A3D. A little bit tougher than just that dotted decimal notation, because we're talking about much bigger numbers, 128 bits instead of just 32 bits. Okay, now what do we do with addresses like that? It's still tough, even with just 32-bit mass. It's still tough to address everything to that many numbers, like 4 billion numbers. So part of every IP address identifies the network, and part of it identifies the local computer, the host on that network, because the internet is based on having networks, local area networks, that are connected to each other. That's the inter part of the internet. And in a local area network, the IP addresses all start the same. There's a subnet mask. Here's a typical subnet mask, 255.255.255.0. If I wrote this out in binary, 255 is 8 ones in a row. So I get 8 ones in a row, 8 ones in a row, 8 ones in a row, and then 8 zeros in a row, if I wanted to write it out in binary. The parts that are ones are the subnet mask. That means everybody on my local area network has the same address at that point. And the only part that's going to change between my computer on that network and your computer on that network would be the parts that have zeros. So here's an IP address 192.168.4.17. If the subnet mask for that was 255.255.255.0, that means that every computer on this local area network has an IP address that begins with 192.168.4, and then just this last number indicates what the computer is on that local area network. This allows 254 hosts on the network, numbered 1 to 254. IP doesn't let you number 10 or 255. Those are reserved for special purposes. If you need more than that on your local area network, then you have to get a subnet mask that's got more zeros in it and less ones in it. Those are more expensive to get. You have to get these IP addresses and subnet masks from an IP service provider, an internet service provider, an ISP. And they charge more for the bigger ones. Now, who picks the network ID? ISPs assign network IDs to their customers. Where do the ISPs get them? They get an allocation of network IDs assigned by the Internet Assigned Numbers Authority, which is further broken down hierarchically into national, regional, local internet registries. So there might be an internet registry for Southeast Asia, or for Sub-Saharan Africa, or for North America, or for Western Europe. But we don't really like using numbers to access our resources. Even if the numbers become easier, like 192.168.4.17. A domain name server, DNS, maintains a mapping of network names to internet addresses. It's like a big phone book that you can look things up in. So names that you're used to, like www.globalonlineacademy.com, or excuse me, I think that one's .org. Or maybe you've got something like yourname.com because you've built your own website, or youtube.com. Those names get registered and associated with a specific IP address. And over time, it takes about 36 hours, those names get propagated to every domain server, every domain name server in the entire internet. And so new and changed addresses are available for you if you could look it up on a domain name server. And we don't all have permanently assigned IP addresses. The IP address on your smartphone might be different next week than it is today. And it's going to be different when you walk from where you are right now to go to a coffee shop and that has Wi-Fi, and you're connecting to the internet there. You're going to have a different IP address. Some domains have permanently assigned IP addresses called static IP addresses. Like YouTube has a static one for every computer, but most end users, the numbers are assigned dynamically using whatever your local network has as a dynamic host configuration protocol server, DHCP server. You might have seen these names and these initials in error messages or something, not known what they are. What a DHCP server does is it says, hey, I've got these 254 addresses I can hand out. You just connected? Okay, I'll give you the next one. You're .1. The next person that connects, you're .2. Next person that connects, you're .3. You're leased an IP address for a period of time. After that time, it gets renewed or it gets replaced. So you can find out about your own computer. If you're on a Windows machine, bring up a command prompt. You can get that from Windows Accessories, or if you go to the Run, the command prompt you can get with just CMD, and type in the command ipconfig /all. Or on a Mac machine, bring up a terminal window from the Application Utilities folder and type ifconfig. Notice it's ipconfig for Windows, it's ifconfig for a Mac, and the Mac default is already for it to give you all the information. ifconfig doesn't give you everything that ipconfig did, so on a Mac you can also go to System Preferences Network, pick the Advanced tab, and then go to the TCP/IP and the Domain Name Server tabs, and you'll get some of the information that the Windows users got from ipconfig/all. So what does this look like? Here's an example that I ran on my Windows computer. I've got a host name of Steve Toshiba. Guess what? It's a Toshiba machine. And it says that for this particular wireless adapter, for every wireless adapter that's there, it gives information. This is the one that's being used. I've got a physical address. That's my MAC address. Remember, we said those were 48 bits long. Each hexadecimal digit is 4 bits long, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 4, that's my 48-bit unique MAC address. Is DHCP enabled? Yes, it is. That means I'm going to be getting my IP address assigned to me by somebody on my local area network. Here's my IPv6 address. Notice that one's in hexadecimal. Here's the more familiar form, my IPv4 address, 192.168.1.5, with a subnet mask of 255.255.255.0. That means I'm on a local area network that is using 192.168.1 in the beginning of the addresses for everything on the network. The lease was obtained on this date, it would expire on that date. It gives me some information like where my default gateway is. That's what address on my local area network can actually get to the internet. What is the address of my DHCP server? That's the same thing. This happens to be the address of my router. We'll learn more about routers later. Here's a Mac ifconfig example. So I went to my MacBook Air and did ifconfig. And it's telling me, okay, I have an iNet 6, an IP version 6 address of FE80 : That means a whole bunch of zeros and then a 1. That's for whatever this connection LO0 is. Here's the one that makes sense. It tells me my Ethernet address. This is the MAC address, the 48-bit unique hardware identifier. Here's my IP version 6 address, from here up to the % sign. Here's my IP version 4 address. Notice it starts with 192.168.1, just like the one on my Windows machine did, because I happen to be on the same local area network, but this one got assigned an 8. And my network mask, instead of writing it in decimal, it was written as FFFFFF instead of 255, 255, 255. On the Mac, when I do the system preferences advanced and pick TCP/IP, it says I'm using DHCP. Now it gives the subnet mask in decimal, tells me where my router is located. And when I pick the DNS tab, it tells me here's where my domain name server is located. So you can get this information whether you're on a Mac or a PC. Here's some more tools. On both a Mac and a PC, on either the command window in the Windows or the terminal in the Mac, there's a command called NSLOOKUP that lets you get information from the domain name server. If I do NSLOOKUP www.globalonlineacademy.org, it tells me the address is 192.168.1.1. That's my router that I go through to get to anything on the internet. But then it says, okay, and then I go from there to the final place, and it finds a domain called globalonlineacademy.org at address 54.215.223.53, and the domain name server says I can either call it www.globalonlineacademy.org or globalonlineacademy.org. Those names are both associated with this IP address. So let's look up that IP address, 54.215.223.53. And it comes back and it says, oh look, I can get to it via this local address, but here's what you get when you go off to the internet. Here's the address, and it says, here is the name of the computer. Wow, it doesn't say globalonlineacademy.org anymore. It says, you know what? They have chosen to host their website, their domain, on AmazonWebServices.com. And Amazon Web Services has given them this name. Another tool that we'll talk about, you can ping another computer by sending it a useless packet of information, finding out if it got there. So you can think of it as the ping, like on if you've ever watched a submarine movie like Hunt for Red October, you get ping, and it bounces off something and comes back to you. This is, can I bounce some bytes off another computer and come back? You can ping by either IP address or domain name, but warning, some sites have a firewall that blocks ping requests. Some sites don't block them. More and more people are blocking ping requests to prevent a denial of service attack where millions of computers ping the same server at the same time and it gets so bogged down it can't get anything done. A lot of more places should do that, but a lot of them haven't. So, to use ping on either the Windows or the Mac, you type ping and an address, or ping and a server name. You can give the address as an IP address or as the name, like globalonlineacademy.org. On Windows, it sends out 4 ping attempts, and it tells you how long it took for them to come back. On the Mac, it sends out ping requests continuously, so you have to remember to type Control-C or else it'll keep pinging forever. Here's an example. I typed ping 192.168.1.5. That's an address on my local network, and I get things back. Okay, I pinged it with 32 bytes of data. I got 4 replies back. Sent 4, received 4, didn't lose any, and it took 0 milliseconds. Things on my local area network respond very quickly. Then I pinged Ford Motors server, www.ford.com. And it said, okay, I'll do that. And it pinged it at 23.65.17.34. All of them came back, but they were taking longer. 29 milliseconds, 28 milliseconds, and so on. 4 were sent, 4 were received. The average was 32 milliseconds. Then I try and ping www.amazon.com. And it says, okay, I'm trying to ping it. Here's the address. Oh, timed out, timed out, timed out. Never came back. Amazon did not respond to the pings. That doesn't mean that the Amazon server is down. It means Amazon is not going to let me ping things. They don't want to be taken down by a denial of service attack. Now, one of your assignments, this is an individual assignment, not a partner assignment, is assignment 4B. You're going to use the tools from this video, ipconfig or ifconfig, the Mac system preferences if you're on a Mac, the DN or the NS lookup to find domain names, and ping. You're going to be finding your own IP address, the location of your DHCP and DNS servers, the IP address of your school, like Hamden Hall or International School of Beijing, and you're going to experiment with the ping command. So this is kind of a fun assignment. It shouldn't take you very long. So you're ready to do that whenever you're done with this video.